Good morning, children. We are once again back in the P block elements. Among the P block elements, in the last class, we have discussed about group 15. In today's class, we are going to discuss group 16 of the periodic table. Now, the first thing about this group is that we should know the members of this group. This group is called the oxygen family, or it is also called chalcogen. It is called oxygen family, or it is also called as chalcogen. Now, the members of this group are oxygen 8, sulfur 16, selenium 34, tellurium 52, and polonium 84. Electronic configuration oxygen 8 is it has a helium configuration, then 2s2 2p4. Then it has sulfur configuration, that is neon 3s2 3p4. After that it has selenium configuration, that is argon 3d10 4s2 4p4. Then it has tellurium configuration, krypton 4d10 5s2 5p4. And last of all, it has the polonium configuration, that is it has xenon configuration. With that it has 4s14 5d10 6s2 and 6p4. So this is the general configuration. This is the general configuration of group 16 members. Among this, we can see that selenium and tellurium, they contains the D block, and the polonium contains the F electrons. Okay. So now we are going to discuss about the atomic and the physical properties. See, atomic radii, obviously we know that they are smaller than the corresponding elements of group number 15, because as I go along the period, atomic size decreases because of much more contraction of the nuclear attraction. Okay. As the nuclear charge increases, obviously there is a contraction, size decreases, right? Now down the group, they increase mainly due to the addition of a new shell. Next, we oxidation state. Because of high electronegativity and tendency to gain two electrons, oxygen shows oxidation state of -2 only. Okay, and the oxidation state is OF2, whereas it has +2. In H2O2, the oxidation state is -1. All other elements show oxidation states of +2 and +4 and +6. They show +2, +4, and +6 because of the different excitations possible in the empty d orbitals. See, in case of sulfur, it has vacant d orbitals, right? In case of selenium, it has d orbitals, so they can extend their oxidation state to +6 also. Next, we will discuss about the ionization enthalpy. The first ionization enthalpy of these elements are lower than those of the corresponding elements of group 15, despite their smaller atomic radii. So, although they have a smaller atomic radii, but still it is much smaller. This is due to the greater stability of the half-filled orbitals of group 15 elements. Or I can say the ionization E2 values are higher than those of group 15 because of the smaller size of the ions and greater the effective nuclear charge. Okay, greater the effective nuclear charge. After that, we will discuss the metallic character. These elements have very little metallic character because of its high ionization enthalpy. Down the group, the metallic character increases due to decrease in the ionization enthalpy. Thus, oxygen and sulfur are non-metals. So, selenium, tellurium have very little metallic character, while polonium is metallic. So you can well understand oxygen, sulfur, they show non-metallic character, right? Selenium and tellurium, they have very little metallic character, that is, they are intermediate metals and non-metals, and polonium shows a metallic character. So as I go down the group, atomic size increases, as a result of which what is happening, metallic character increases in these members of this group. Okay. Now, electronegativity, these are more electronegative than the group 15. So, if you compare with group 15, we know oxygen is much more electronegative than the group 15 members because of further decrease in size. And hence, as it decreases down the group because of the increase in atomic size, oxygen is the second most electronegative element apart from fluorine. Next, we have melting and boiling point. The melting point and boiling point increases regularly from oxygen to tellurium due to the increase in size and hence greater van der Waals forces. The last element, polonium, has lower melting and boiling point than tellurium because of the maximum inert pair effect. Because of the maximum inert pair effect. Next, we discuss about the chemical properties. Anomalous behavior of oxygen. What we have noticed, the anomalous behavior of oxygen is due to its small size, high electronegativity, and absence of d orbital. See, this is such an element which is actually a non-metal. Being a non-metal, why it shows a behavior which is totally different from the other members of this group. It is because of the absence of d orbitals in oxygen limits its covalency to 4. It limits its covalency to 4. Now hydrides, they form hydrides of the formula H2E. See, the hydride of oxygen is H2O, hydride of sulfur is H2S, hydride of selenium is H2AC. So it forms hydride. The properties of hydride, thermal stability. It decreases down the group because as the size of the atom increases, the bond dissociation enthalpy actually decreases. Bond dissociation enthalpy actually decreases. Okay. After that, we are going to start the next part of the chapter is the acidic character. Now, what we know that it increases down the group because they are dissociate into corresponding hydrogen and see H2E. Any of these will dissociate into H plus He minus. He minus will dissociate into H plus E2 minus. Next, we have reducing character. Except water, all a reducing agent and reducing character increases down the group. Boiling point and volatility. H2S has a higher boiling point because of hydrogen bonding. Because of hydrogen bonding, after the sudden drop from H2O to H2S, the boiling point gradually increases from H2S to H2T because of increase of molecular mass and hence van der Waals forces. Okay. Now we would discuss about the first acid of this group is sulfuric acid. Now, see, sulfuric acid is also known as king of chemicals, right? Apart from sulfuric acid, number of other acids we have. That is sulfurous acid, H2SO3. We have sulfuric acid. We have peroxydisulfuric acid. Right now, our study is restricted to the study of sulfuric acid. Sulfuric acid is called king of chemicals. It is also known as oil of vitriol because of its oily nature. Now, manufacture of H2. So, for sulfuric acid is manufactured by the contact process, which involves the following equations. What is, say, sulfuric acid manufacture? It is manufactured by the contact process. What happens in the contact process? First of all, we take any sulfur containing compound. It can be metal sulfide or it can be sulfur directly. Now, when the metal sulfide is reacted to oxygen, we get what? Sulfur dioxide. Now, the sulfur dioxide is made to react with oxygen here. The most important thing, the catalyst here is vanadium pentoxide, okay, V2O5, and we get sulfur trioxide, SO3. Now, the sulfur trioxide made to react sulfuric acid, we get H2S2O7. We get H2S2O7. This H2S2O7, this compound H2S2O7 is actually called as oleum. This compound H2S2O7 is called as oleum. Now, oleum is diluted with water and we get sulfuric acid of the desired concentration. So just remember that if I have to prepare sulfuric acid, first of all, what we do, we oxidize sulfur containing compound sulfur dioxide. The sulfur dioxide is further oxidized to sulfur trioxide. Here we need a catalyst, and the catalyst here is vanadium pentoxide. Okay. Now the sulfur trioxide that we obtain, that is made to react with sulfuric acid to give us H2S2O7, which is called oleum. Oleum is further diluted and we get sulfuric acid. Now we are going to discuss the properties of sulfuric acid. Now we are going to discuss the properties of sulfuric acid. See one thing, Sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84. Okay, it has a specific gravity of 1.84 at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin, right? Because of its low volatility, concentrated sulfuric acid can be used to manufacture more volatile acid than from their salt. See this reaction, we have metal halide MX that is made to react to sulfuric acid, we get HX plus M2SO4, we get HX plus M2SO4. This M is the metal and here we have X. X can be any of the halide, it can be fluorine, chlorine or NO3. So what is the reaction? We take a metal halide, react that with sulfuric acid, we get a halo acid and we get the corresponding metal sulfate. So here what is the reaction? It is simply exchange of acid. Now see sulfuric acid is a powerful rehydrating agent. So that's why see any compound that contains sugar, that is in this case we have taken a compound C12H22, that on reacting with sulfuric acid only what am I getting actually? That is C12H22O11. That is a complex sugar, or I should say a disaccharide. These disaccharide on being reacting sulfuric acid, it extracts the molecule of water, and we get actually metallic carbon come of, or I should say carbon comes out. As carbon comes out, it is called as charring of sugar. So one important use of sulfuric acid is that sulfuric acid is used to extract water from a substance. As a result, the black mass is left out, and this black mass is called charring. And the process is called charring. Is this part clear to you, children, now? Okay. After that, we have hot concentrated sulfuric acid is moderately strong oxidizing agent. Is a moderately strong oxidizing agent. Some of the important reactions are as follows. Copper is made to react with sulfuric acid. We get copper sulfate, sulfur dioxide plus water. Sulfur is made to react with sulfuric acid. We get sulfur dioxide plus water. Carbon is made to react with sulfuric acid. We get carbon dioxide, sulfur dioxide plus water. We get carbon dioxide, sulfur dioxide plus water. We get carbon dioxide, sulfur dioxide plus water. This is how the reaction takes place. Okay. After that, we have next compound we would be studying is dioxygen, which is called as O2. How dioxygen O2 is prepared? It is prepared simply by the following reaction. See, we take a very good oxidizing agent like potassium permanganate, right? Color of potassium permanganate is a purple one. That is heated. We get potassium manganate, manganese dioxide plus oxygen. We have taken potassium permanganate, that is heated. We get potassium manganate, manganese dioxide plus oxygen. Now, next reaction we have is we can simply take potassium nitrate, which is a solid that is heated strongly. We get potassium nitrite and oxygen gas is given out. Next, we have laboratory preparation. In laboratory preparation, we take potassium chlorate. Potassium chlorate is heated in presence of manganese dioxide at a temperature of 420 Kelvin, which react with manganese dioxide temperature of 420 Kelvin. We get potassium chloride plus oxygen. We get potassium chloride plus oxygen. So what is the reaction? The specific reaction is that we have potassium chlorate. This potassium chlorate is heated with manganese dioxide temperature of 420 Kelvin. We get potassium chloride plus oxygen. That is one of laboratory preparation of oxygen. Next method we have is the thermal decomposition of oxides of metals low in the electrochemical series and higher oxides of some metals are obtained. That is, we have Ag2O that is made to react with silver in presence of oxygen, right? That is, we have Ag2O silver oxide that is heated strongly, we get metallic silver and oxygen. We have Pb3O4 that on heating we get PbO plus oxygen. We have mercury oxide that on heating will give you mercury and oxygen. Next reaction, we have lead oxide that on heating we get PbO plus oxygen. So we have PbO2 that on heating we get PbO plus oxygen. So these are the methods by which we can obtain oxygen. Next is by the composition of hydrogen peroxide. Hydrogen peroxide is a highly reactive compound that is heated and we get water and oxygen. Actually, it doesn't need a long amount of heating. With a small rise in temperature, it dissociates into water and oxygen. So this is another method by which oxygen is obtained. This is another method by which oxygen is obtained. Industrially, dioxide is obtained by liquefaction of air followed by fractional distillation. So just remember, industrially, in the industry, industrially it is prepared simply by the liquefaction of air followed by fractional distillation. The air, what we know, contains approximately 20% oxygen and 80% nitrogen. So air is a great source of oxygen. This great source of oxygen can be used. But the process applied is fractional distillation. I hope you have understood. I'm giving you 2 minutes time. Just copy down this reaction, children. I hope children you have copied it. Okay, after that we are going to discuss the properties of dioxygen. What are the general properties of dioxygen? See, dioxygen is a colorless, odorless gas. It liquefies at 90 Kelvin and freezes at a temperature of 55 Kelvin. Some of the reactions of dioxygen with metals and non-metals and other compounds are given below. See the reaction. The reaction is calcium is a highly reactive metal that reacts oxygen to give CaO. Aluminium reacts oxygen to give Al2O3. Phosphorus with oxygen to give P4O10. HCl with oxygen in the presence of a catalyst CuCl2 that gives you Cl2 and water. That gives you Cl2 and water. So what are the properties? The first property is it is a colorless, odorless gas. It liquefies at a temperature of 90 Kelvin and freezes at 55 Kelvin. Some of the reactions of dioxygen with metals and non-metals and other compounds are given below. So calcium with oxygen, we get calcium oxide. Aluminium with oxygen, we get Al2O3. Now phosphorus with sulfur dioxide, with oxygen, we get actually P4O10. Next, we are discussing a binary compound oxygen. Another element is called oxide. Now, the next topic we are discussing about oxide. Now, what is an oxide? Oxide is a binary compound formed by the combination of metal or non-metal with that of oxygen only. So, just remember, oxide is a binary compound that is formed by the combination reaction of an oxygen with a metal or that of a non-metal. That is called as oxide, right? Now, there are different types of oxides. Some of them are called acidic oxide, some of them are called basic oxide. Just remember that non-metals give acidic oxide and metals give basic oxide. So, if you want to write down definition of acidic oxide, please write it down. Those oxides which are of non-metals are generally acidic and they are called as acidic oxides. So acidic oxides are generally oxides of non-metals. Next, make the next heading basic oxides. These are oxides of metals. So the oxides of metals are basic in nature and they are called as basic oxide. Oxides of metal are basic in nature and that is called as basic oxide. Oxides of metals are basic in nature and that is called as basic oxide. Okay. After that, the next oxide we have is neutral oxide. Oxides which are neither acidic nor basic in nature, they are called as neutral oxide. Example of neutral oxide is carbon monoxide. Another oxide is N2O. Then the next oxide is NO. So nitric oxide, nitrous oxide, carbon monoxide, water. All these are examples of neutral oxide. Why are they neutral? Because they're neither acidic nor are they basic in nature. So they are called as neutral oxide. After that, we have the next ox that is called amphoteric oxide. Amphoteric oxides are those oxides which shows both acidic as well as basic behavior. Those oxides which shows both acidic as well as basic behavior, they are called as amphoteric oxides, right? So amphoteric oxides are those oxides which show both acidic and basic behavior. Now see, next part we have is an acidic oxide reacts with water to give an acid. Example is sulfur dioxide plus water, we get H2SO3. As a general rule, only one non-metallic oxide, that is carbon dioxide, sulfur dioxide, N2O5, Cl2O7, are acidic, but oxides of some metals in higher oxidation state also they show acidic character. So just remember, children, that in general what we see, that non-metallic oxides are basic and metallic oxides are non-metallic oxides are acidic and metallic oxides are basic in nature, but certain exceptions are there. That is, see, Cl2O7 is acidic. Okay. Now we have acidic character. For example, some oxides of metals are also acidic. For example, Mn2O7, CrO3, V2O5. Oxides will combine with water to form base is called basic ox in general. Metallic oxides are basic. See one example, calcium oxide plus water, it forms calcium hydroxide. Calcium hydroxide is a strong base and is alkaline in nature. Is this part clear to you now, children? Please make it clear. I hope this portion is clear to you, children. Okay, I'm giving you 2 minutes time. Please copy down these reactions. Then we could move to the next part of the chapter. I hope, children, you have copied it. See, after that, we are moving to the next part of the chapter. Next part of the chapter we will discuss is the study of ozone. How ozone is prepared. See, ozone is prepared by subjecting pure and dry oxygen to a silent electronic discharge. So just remember, ozone is actually one allotropic form of oxygen. Ozone is actually one of the allotropic form of oxygen. Ozone is prepared by passing oxygen, pure oxygen, and oxygen should be dry in a silent electric discharge, right? Now, what is the structure of ozone? Very important for exam point of view. Now, what we see that ozone is actually has this specific structure, that is oxygen double bond or single bond. That actually that actually resonance, it has resonating structure of this. Okay, so this is the structure of ozone. Now it is a resonance hybrid, and what is the bond angle? Bond angle is 116.8 degree, and the what is the bond length? Bond length is 127.8 picometer. Okay, so this is actually the resonance hybrid of and because see ozone actually shows two resonating structure, and this is the resonating hybrid structure. Now ozone is a pale blue gas which has a strong characteristic smell due to the case with which it liberates atoms of nascent oxygen. So I can say that ozone is a powerful oxidizing agent. Why? Because ozone actually dissociates and gives you O2 plus nascent oxygen. Because of the presence of the nascent oxygen, what happens? It is a better oxidizing agent than other members. Okay, now what is the uses? Ozone is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching oil, ivory, and flour and starch. Oil, ivory, and flour and starch. So that are some of the uses of ozone. Next, we have the next compound is sulfur. Sulfur forms numerous allotropes, of which the yellow rhombic and monoclinic are the most important. Both the rhombic and monoclinic sulfur, they have S8 molecules. So as you could see, the first structure, that is called the puckered ring-like structure of sulfur. Next is we have the chair structure. Okay, these are two important structure of sulfur. So I can say that sulfur exists in two of the allotropic forms, and these two allotropic forms of sulfur are puckered sulfur, other is the chair structure of sulfur, and these two structures are the most predominating structure of sulfur. Okay, is this part clear to you, children? So that I can say is a nutshell of the study of the group 16 of the periodic table. The next part is left out is sulfur dioxide. See, sulfur dioxide is prepared by reacting sulfur in presence of oxygen to give sulfur dioxide. In the laboratory, it is prepared by treating sulfide with dilute sulfuric acid. Take a metal sulfide, in this case, we have ferrous sulfide, that is made to react with oxygen. We get Fe2O3 and sulfur dioxide gas is coming out. Now, the next part we have is the properties of sulfur dioxide. The properties of sulfur dioxide. So here we have what are the important properties of sulfur dioxide. Sulfur dioxide is a colorless gas with a pungent smell and is highly soluble in water. Colorless gas with a pungent smell, highly soluble in water. Its aqueous solution is acidic and it turns the blue litmus red. It reacts readily with sodium hydroxide solution to form sodium sulfide and sodium hydrogen sulfide. Okay, sodium hydrogen sulfide. Next reactions, we have sodium hydroxide, sulfur dioxide, which it forms Na2SO3 plus water. Now, Na2SO3 that is made to react with water and sulfur dioxide, we get sodium hydrogen sulfide. So there are two basic reactions, sodium hydroxide plus sulfur dioxide, that gives Na2SO3 plus water, Na2SO3 with water and sulfur dioxide, it forms sodium hydrogen sulfate. Okay. Now, the next part is that dioxide reacts with chlorine. See this reaction, very important reaction. Sulfur dioxide reacts with chlorine in presence of charcoal to give SO2Cl2. Sulfur dioxide plus oxygen in presence of vanadium pentoxide, it forms sulfur trioxide. Okay. In the presence of moisture, it liberates nascent hydrogen and thus acts as a reducing agent. So we have Fe3 plus, that is made to react with sulfur dioxide and water, we get Fe plus 2, SO4 minus 2 plus 4 H plus. Okay. After that, with next reaction, that is sulfur dioxide plus MnO4 minus plus water, we get sulfate ion. Now, sulfur dioxide is also a resonating structure. You have these two structures, sulfur double bond O single bond oxygen. Then we have double bond and a single bond. They have resonates and we get this structure. Next part we have uses of sulfur dioxide. Sulfur dioxide is used for the refining of petroleum and sugar, in the manufacture of sulfuric acid, calcium hydrogen sulfide, and sodium metabisulfide, as an anti-clot, disinfectant, and preservative in the bleaching of wool and silk. These are some of the uses of sulfur dioxide. Okay, children, I hope you have understood this chapter. I give you 2 minutes time. Please copy it. After that, we'll end. We hope to end the chapter here. So in a nutshell, I have discussed with you the total characteristic features of the group 16. It mainly consists oxygen, sulfur, selenium, tellurium. We have to study some of the important compounds. In this, we have studied about oxygen, ozone, sulfuric acid, sulfur dioxide. Okay. Okay, children, that was all for the day. Thank you.